Well, if not, then I will talk to you about one problem for the whole class, and that will be, well, I will approach the problem from, again, from three different points of view. As usual, algebra, geometry, physics, and those are going to be a little bit more complicated as in comparison to what we had before. So the problem is coming from applications. So the problem is the following: if you have some data, and if you, for example, graph the data, and you have data coming in pairs, so two values are coming together, and you sometimes graph the data to see what happens, and as you graph, you see those points, and then as you plot all these points, you see that those points make sort of a line. And then what you want is to decide what is the line. If you were to say the data makes a line, what should be the line? And that the result will be called best linear fit. Because you are asking for a line. If you were to ask about parabola, that would be best quadratic fit, or best exponential fit, or whatever you see that seems to be a parabola, exponential function, or linear. Well, you try to fit that data into this narrow class of functions. So that means that you are looking for an equation y equals mx plus b, and you don't know what m is, you don't know what b is, and all you want is that line to fit somehow the data. Now the idea is that you usually don't do it on paper, because usually your data is coming in such a quantity that you just don't see it and plot, or even plotting, it's sometimes hard to see all the points together because they're so scattered. So what we are looking for is a method of finding that line algebraically, because that way you can process the data on a computer and get the result quickly. And you should think about it as a method that would work for a lot of different sets of data, as long as you want linear fit. So that it's not that just only one experiment that you process and you do one-time decision by choosing that line. It's something about method of choosing the line for many, many, many different data. So how do you do that? What's the setup? What's the algebraic setup? Well, algebraic setup is that there is something you wish for. You wish that all these points belong to one line. And that would be an ideal situation if you have them exactly aligned. And that means that let's say, before I do algebraic equations, I will have to have notations. So x1, y1 is the first point, x2, y2 is the second point, and so on. And you have many of them, xn, yn. Think of n as large, so you have the whole cloud of points there. So then the ideal thing would be to have y1 equals mx1 plus b, y2 equals mx2 plus b, and finally yn equals mxn plus b. And if it is possible to satisfy this system, you just set up the system, solve it for M and B, because those are the only unknowns in the system. But in reality, you don't expect data to fit one line, and in reality, having a lot of equations but only two unknowns, you don't expect the system to have a solution. This is so-called overdefined system. There are too many conditions to satisfy. Now, what is it that is reasonable to hope for?
You have the least error.
Exactly. So you say that you don't even hope for exact equalities. You have approximate equalities. So instead of that difference being 0, and that difference being 0, and that difference being exactly 0, you say, well, instead of 0, I would allow some errors. And those differences will be error 1, error 2, error n. But then you see there is a problem. You have too many variables. Because at this point for this system, you don't know what these errors are. Right? And how would you solve a system in this case? So the idea is not about solving the system. The idea is to figure out one parameter, one measurement of how bad or how good this solution is, or this set of errors is. So you have a bunch of numbers, error 1, error 2, error n. How would you decide, okay, well, this is a good set of solutions, or it is not good?
It's like the, if you square those, and then it's like the least.
So why don't you just add them up and say that this sum should be small? Well, that's the problem, exactly. If you have some errors positive, some errors negative, they may cancel, resulting in a small sum, but actually large errors. So if you square all of them, then what you have is one single parameter to look at, and making that parameter small ensures that all the errors are small, and therefore the approximation is small. And then, so what is it that I have here? I have exactly those differences. So I have a sum from I equals 1 to m of the values yi minus mxi plus b squared. So we look at some of those squares, and we want to minimize that sum. Well, minimize using what? Yi's are constants given, right? Xi's are given constants, so you minimize using m and b only. And this is exactly the point where a function of two variables comes in place. And you never thought about a function of two variables until this point. Right? So it shows up naturally. And that is a function of m and b. And you allow m and b to be any real values, right? There is no restriction on m and b. You're searching for all possible pairs. And among all possible pairs, you're choosing the one that minimizes this function. And then we know how to do it, right? So if you want to minimize a function of two variables, you say the gradient of f has to be 0. You're looking for critical points, and then it means you have to find the partial derivative of f with respect to m. You have to find the partial with respect to b, equate them to 0, and solve the system. So can we find partial of f with respect to m. Because the formula is given. The formula is simple. It's going to be a sum. You'll have to differentiate each term separately. So the derivative is going to be sum from 1 to m of derivative of that square with respect to m. Well, derivative of a square is going to be 2 times yi minus mxi plus b. And that should be multiplied by partial of that quantity inside with respect to m. And what's that? Negative xi, that's correct. So you equate that to 0. And then partial with respect to b is a similar thing. You have a sum of derivative of the square, so it is yi minus mxi plus b, multiplied by partial of that with respect to b. Which is what? No, partial of this with respect to b. Negative 1. That's right. And that sum is equal to 0. And you have a decent system of 2 equations, 2 unknowns, which is solved. And notice that the equations are very simple in the sense that they are linear on the unknowns. Unknown is m, and every time you make this summand, m shows up in degree 1, b shows up in degree 1, and the same story here. So you have a system of 2 linear equations on 2 variables. Very, very simple thing.